What lies at the heart of a black hole? Hello, and welcome to Cosmic Enigma. Imagine a place in the universe where time itself warps, where gravity is so immense that nothing, not even light, can escape. This isn't science fiction. This is the reality of black holes, some of the most mysterious and extreme cosmic objects known to existence. They challenge our everyday understanding of reality, pushing the boundaries of physics to their limits. But what truly lies at their very heart? What happens to everything that falls in? The answers are far more complex and mind-bending than you might initially imagine. Our journey begins at the event horizon. This isn't a solid surface, but a boundary in space-time, the ultimate point of no return. Cross it, and you're irrevocably committed to falling towards the center, with no possibility of escape. To understand this, think of Einstein's general relativity. It tells us gravity isn't just a force, but the curvature of space-time itself. Imagine a stretched rubber sheet. Place a bowling ball on it, and it creates a depression. That's how mass warps space-time. For a black hole, the mass is so immense that this curvature becomes infinitely steep, creating a hole in the fabric of space-time from which escape is impossible. So if light can't escape, how do we see black holes? We don't observe them directly. Instead, we detect their profound influence on their surroundings. The most spectacular observable phenomenon is the accretion disk, a swirling, superheated ring of gas and dust spiraling inward. The intense friction heats this material to millions of degrees, causing it to glow brightly, especially in X-rays. This is how astronomers detect them, like Sagittarius A, at the center of our Milky Way. Just outside the event horizon is the photon sphere, where gravity is so strong that light particles can orbit the black hole in unstable paths. Some escape, contributing to the glowing edge seen in images from telescopes like the Event Horizon Telescope. Some black holes even eject powerful jets of charged particles at near light speeds. Before we go deeper, let's debunk some common myths. First, black holes are not cosmic vacuum cleaners that indiscriminately suck everything in. Their gravitational effects, from a distance, are no different from any other object of the same mass. If our sun magically became a black hole, Earth would continue to orbit it exactly as it does now. Second, despite their name, black holes are not entirely black. While light can't escape from within the event horizon, those superheated accretion disks glow intensely. The famous M87 black hole image shows a dark shadow against a brilliant glow. Finally, black holes are not all the same size. They range from stellar mass, collapsed stars, to intermediate mass, more mysterious, to supermassive black holes at galaxy centers, millions to billions of times the sun's mass. As you venture past the event horizon, the journey leads inexorably towards the black hole's very core, the singularity. According to Einstein's general relativity, this is a point of infinite density and zero volume, where all the black hole's mass is concentrated. It's the ultimate endpoint for all matter, crushed into an infinitesimally tiny point. At the singularity, the curvature of spacetime becomes infinite, and the laws of physics, as currently understood, fundamentally break down. It's like trying to divide by zero. The result becomes undefined. This breakdown isn't just a theoretical curiosity, it's a profound limitation of general relativity itself. It signals a critical juncture where classical gravity must be reconciled with quantum mechanics, the theory governing the universe at its smallest scales. This is the final frontier for theoretical physics. Before reaching the singularity, an object falling into a black hole would experience one of the most bizarre and terrifying phenomena: spaghettification. This is a real scientific term. It describes the extreme vertical stretching and horizontal compression of an object into a long, thin, noodle-like shape. This gruesome transformation is caused by intense tidal forces. It's not just gravity's strength, but the difference in gravitational pull across an object. Imagine falling feet first. The gravity on your feet would be vastly stronger than on your head. This differential pull stretches you vertically, while forces pulling on your sides compress you horizontally. For smaller black holes, spaghettification would tear an object apart, before it even reaches the event horizon. But for supermassive black holes, the event horizon is much larger, and the gravitational gradient is less steep at that boundary. You could theoretically cross it without immediate squashing. But once inside, spaghettification is inevitable as tidal forces rapidly increase closer to the core. For decades, black holes were thought to be eternal cosmic prisons. But in 1974, Stephen Hawking proposed a revolutionary idea. Black holes aren't entirely black, but actually emit radiation and slowly evaporate over incredibly long timescales. This is Hawking radiation, arising from the interplay between gravity and quantum mechanics. It's explained by virtual particles constantly popping in and out of existence in empty space. Near the event horizon, if one particle of a virtual pair falls in, its entangled partner can escape, becoming a real particle. This escaping particle carries energy away, causing the black hole to slowly lose mass. For massive black holes, this is incredibly slow, taking longer than the current age of the universe. Hawking radiation revealed a profound conflict, the black hole information paradox. General relativity suggests information about matter falling into a black hole is lost forever, leaving no trace in the emitted radiation. This is supported by the no-hair theorem, which says black holes are only defined by mass, charge, and spin, forgetting other details. But quantum mechanics insists that information is always conserved. It can be transformed, but never truly destroyed. The idea that a black hole could destroy information challenges the very fabric of quantum theory and the deterministic nature of physical laws. This paradox is a central challenge in the quest for a unified theory of quantum gravity. The information paradox has spurred intense research and some wild theories. One controversial idea is the firewall hypothesis. It suggests a searing firewall at the event horizon that would incinerate anything crossing it, destroying information at the boundary. However, this directly violates Einstein's equivalence principle, which states that free-falling is indistinguishable from floating in empty space. A more elegant approach is the holographic principle. Rooted in string theory, it suggests that all information about matter falling into a black hole isn't lost, but projected and stored on the two-dimensional surface of its event horizon. This is inspired by the fact that a black hole's information content is proportional to its surface area, not its volume. It suggests our 3D reality might be an emergent property of information on a 2D boundary, like a hologram. Another compelling framework is the fuzzball theory. This radical alternative proposes that black holes aren't points of infinite density with a sharp event horizon, but extended, grainy, or fuzzy objects made of a complex, messy ball of strings. In this model, information isn't destroyed but distributed within the quantum state of this fuzzball. From the outside, it mimics a traditional black hole, but internally, information is preserved. The quest to understand what lies at the heart of a black hole remains one of the most profound and active frontiers in theoretical physics. It's a journey into the unknown, where our most successful theories collide and reveal their limitations. The singularity points to the need for a more complete theory of gravity at extreme scales. Spaghettification vividly illustrates the bizarre power of differential gravity. But it's the black hole information paradox that truly drives the contemporary search for answers. It challenges our fundamental understanding of how the universe works and whether information, the very building block of reality, can ever truly be destroyed. While significant progress has been made, a definitive answer remains elusive. It may indeed take decades before humanity truly unravels this cosmic secret. The resolution of this paradox and a comprehensive understanding of black hole interiors are central to the ultimate goal of finding a unified theory of quantum gravity, a single framework that can seamlessly describe both the macroscopic universe governed by gravity and the microscopic world of quantum particles. This grand endeavor promises to unlock unprecedented insights into the fundamental nature of our universe, from its very origins to its ultimate fate.